edits. Okay. So I wanted to talk about some of the homework problems I gave last time. I don't know if you haven't looked at them yet, but it had to deal with actually doing arithmetic and setting the various flag registers or condition codes. And we will try to work through an exercise today on assembly language programming too. But so we have these various condition codes, or they're also called flags or flag bits, and the status register. And on page 10, and I'll list them here, he gives the conditions under which these flag registers, or flag bits rather, are set. And this is for 32-bit arithmetic. And you can do an add, and if you put the S subscript, that means set the corresponding bits in the register. Otherwise, they're not set. But this actually would correspond, if the 31st bit is set, if we treat that as a signed number, that would mean that R is less than 0. So whether it's an unsigned or signed, whether you're adding two signed or unsigned numbers, if bit 31 is 1, then the end flag is set. Okay. You have to keep track of whether that's actually a negative result or not. You know, it may not be if you're treating that as unsigned. And then the condition for the 0 flag, if you look at his definition on this page, it's R31 bar ANDed with R30 bar ANDed with R0 bar. That essentially means that it is only set if all the bits in the register are 0. Okay. Equivalently, mathematically, the condition would be R is equal to, the result is equal to 0. That's when the 0 flag is set. Anytime you do it. Here I'm using addition, and we'll work through some examples here. But any sort of mathematical operation, okay, and if the result is 0, then the 0 flag is set. The ones that are a little bit trickier are the carry, and it is it's set if A31 and B31 are both set, which means that they're above, half the value that the number can contain. When you add them, that will result in carry. So if the two most significant bits are both 1 and you add them, that'll generate a carry. Or let's see, if A31 and is set and R31 is not set, or B31 is set and R31 is not set. And I'll put what that actually means kind of mathematically in just a second. So the carry here is also the unsigned overflow. And then we also have the V flag, the signed overflow. And it's set under these conditions. If A31 and B31 are both set, but you do this at arithmetic operation, and R31 is not set, okay, or they're A31, B31 are not set, but R31 is set after the addition. So what this means is C is set if the unsigned result is less than the unsigned sum. In other words, the carry flag is set if there's an error. Okay? If you look at the 32-bit number and it's not equal to the sum of the two 32-bit numbers, okay, using unsigned arithmetic. And then the overflow flag is set when A and B have the same sign and R has the opposite sign. So if you add two positive numbers, you should get a positive result. If you add two negative numbers, you should get a negative result. The V flag is set if that doesn't happen. Again, that there's an error that occurred. Now, you never have to worry about overflow when you're adding A and B and one is positive and one is negative. Okay. There's no way you can get an overflow when you're adding a positive and a negative number, because the sum will always be smaller than whatever the largest is. Okay. So let's, now instead of working with 32-bit numbers in the homework, he has you work with 8-bit numbers. And sometimes he gives them in hexadecimal, sometimes he gives the value of decimal, might be a signed decimal. You know, always, you know, 2's complement arithmetic, or the 2's complement representation is used to store the number internally. You know, it's always stored in binary. But let's look, because I don't want to write down 32-bit numbers, let's consider, you know, 8-bit addition. But so R7, or the 7th bit, is actually our signed bit. So A, B, and R. So 30. So here in 8-bit arithmetic, we can represent unsigned the numbers 0 to 255. Okay, 00 to FF in hexadecimal. Our signed range is negative 128 to plus 127. Okay, still 256 numbers. We have to keep track of whether the numbers are actually signed or unsigned. So here, if you add these, you get 80 NZBC. It's not negative. It's not 0. There was no overflow. These are both valid. They're both represent 30 and 50 in both the unsigned and signed representations. They're both within the range 0 to 255, and then also in the minus 128 to plus 127. There's no overflow. There's no carry. So after adding those two, if you looked at the flags, and remember what we typically have to do is we carry out some sort of branch instruction. Branch BN, branch if the result is negative. BZ, branch if the result is 0. Here, if you added, and again, I'm writing the results in decimal here. But, you know, if, first of all, well, let's talk about this. R here, if we treat it unsigned, it's 150. But if we treated this as a signed addition, 100 plus 50, 150 and 2's complement, that number, 150, is actually represents 256, 256 minus 150. My brain's not working. 106, negative 106, as a 2's complement number. Again, 150, whatever the hexadecimal representation that is, that'd be 128, you know, no 64s, no 32s, but you know, we could come up with, if you could convert that to the corresponding hexadecimal representation, but I'm writing it out in binary here. But because this is greater than 128, bit 7 would be set, right? Because bit 7 is set, that means that n would be set, indicating we got a negative result in 2's complement arithmetic. It just looks at that most significant bit. And if in 8-bit arithmetic, if we're greater than 127 here, that 8th bit is set. So that would be interpreted as a negative result. You would ignore that if you know these two numbers are unsigned, because you've got the right value. It's not 0. Now, what are the conditions for overflow for signed? Well, 100 plus 50, that's greater than 127. That's an overflow, right? We can't represent the value positive 120 in an 8-bit number using signed arithmetic, using a signed representation. That value actually represents a negative 106. So we got an incorrect result if we treated these signed. To add these two numbers, treating them signed, we'd have to go to a longer word representation, 16 bits or 32 bits. So we got an overflow. There was no carry. There is no carry here because it doesn't exceed 255. It's essentially the condition for a carry. Okay. In other words, the result we got is correct if we treat this as unsigned arithmetic, but it's incorrect if we treat these two as signed numbers and treat the result as signed. So it's an error if we're treating them as signed, so that D flag will be set. And that's what this is doing. We've got the case here where, again, these are all 7 bits because we're working with 8-bit. It's unsigned, A7 is not set, B7 is not set, but the result signed bit is set. So this would be equal to 1, the D flag is set. So you can get a little lost here in the Boolean algebra, but basically the C flag is set if there's an error doing unsigned arithmetic. The overflow flag is set if there's an error doing signed arithmetic. So here, this is an error if we treat this signed. It's not an error if we're doing unsigned arithmetic. 100, 250. The result here would be 350. So that's a much greater value than we can represent in either signed or unsigned. So it actually rolls around. The result would be 350 minus 256. So the value that would actually be on our register is 94. The 350 minus the 250 minus 256. That's the number that would be in the register. It's not negative. Okay. It would have to be in the range of 128 to 255 to be treated negative. It's not 0. There was a carry, right? Went from 100 to 250, that generates a result that's greater than 256. There's a carry. The question is, what about if we treat that as an unsigned, or I'm sorry, if we treat those two numbers as signed, is that an error? Well, in signed arithmetic, 100 is 100, but the value 250 in register B is actually treating this as a signed number That's actually a -6, right? 2's complement, 256. Remember, anything in the range 128 to 255 is actually a negative number. 250 is actually a -6. So we got the result of 94. Is that wrong if we treated this as a signed addition? 100 plus a -6 is 94. So in that case, the overflow flag would not be set. We got an error doing if we were treating those two numbers as unsigned, because 100 plus 250 won't fit in an 8-bit result. But if these are actually signed numbers, this is really not 250. It's really -6, right? And 100 plus a -6 is a 94. And so we got the correct result. And so the V flag would not be set in that case. Questions? Is that okay? Yes, no? We can do some other. Okay. So 100 plus a -100, B here as an unsigned number would actually be 156, right? So, and I probably should have, I could have written 156 here. That's equivalent. Okay. But 156 represented in decimal is the equivalent to -100 in 2's complement notation. When I add these two, I get 0. That's not negative, but it is 0. So the 0 result would be set. Now, do I get an overflow? You never have an overflow. Again, the overflow, you always treat the two numbers as 2's complement. You never have an overflow when you add a positive and a negative. You can only get an overflow when you're adding two positives or two negatives. So if I treat this as a positive number, I'm sorry, as 2's complement, -100, I'll never get an overflow. But what if I were treating this as unsigned? I wouldn't treat that as -100. If I were treating that as an unsigned number, it's the same number, the same bits in the register. But if I treat it as unsigned, it's really 156. It's not -100, right? In that case, 100 plus 156 gives me 256, which would be a 1 and 8 zeros. So my result is still 0. Same result I get using 2's complement arithmetic. But in that case, there's a carry because I exceed the 255 limit there. Okay, so I don't know, maybe it helps here if I said here this is actually, let's say 156. Okay. And similarly, this is -100 is 156 unsigned. Similarly, 250 is -6 and 2's complement notation. Okay. There's the way the flags are set, how you interpret the numbers is, I mean, that is what you have to keep track of as a programmer. Okay. So, if you were treating this as, what's the example here? You're treating this as both unsigned numbers, add those, you get the right result. There's no error there. But if you're treating them as signed, we got a negative answer. So that would be an incorrect. We could check the V flag to see that we overflowed in that case. So I think one of the homework problems I assigned last time has you fill out this table like this, setting these flags. And then there's another example where it has you set the flags using subtraction. You don't have to do anything different there. The way we subtract using a computer is we add the 2's complement. So on that problem where he's got the A and B, you'll probably want to make another column where you can mark down the 2's complement of B. And then you add A and the 2's complement and use the same rules. Is that clear? No? Yes? Okay. The stack is an area in RAM. Remember in this microcontroller. Unlike on your PCs, on this microcontroller, we've got flash ROM that holds our program. We can also store constants there. And then we've got, I think in this microcontroller, it's 64 kilobytes of RAM that we can use for data storage, read-write storage. The stack is an area in RAM that we can read and write to, and it's used for local variables in a function, and we can use it. You can use it anytime you want for just temporary data storage. Remember, when we call a function, we can lose the values in R0 through R3. Okay, you may want to push those onto the stack. All the other register values have to be preserved. How are they preserved? Inside the function, if R5 is used, it's actually pushed onto the stack to be saved, and then they might use register R5, and then before the function return, they pop it back off the stack back into R5. So the stack pointer So it's really convenient. You don't have to go through the process we talked about last time of having, defining locations in memory and setting up the pointer and that's actually what you would do for global variable storage. In C, anytime you write a function and it's just int, that variable is actually never named. If it's int x, it's not stored at some location x in memory. It's actually stored on the stack. And it's never addressed by name. It's just addressed by an offset relative to the stack pointer. So the stack pointer contains the address of the last data item pushed on the stack. Now, the convention almost with all microcontrollers is the stack pointer, when you push something onto the stack pointer is actually decremented. Okay. So like in RAM on the microcontroller, the stack pointer is actually usually points to the top of RAM, and then you set aside an area that's used for the stack, and then the bottom part of RAM is used for, like the variables and stuff that we've used. So essentially, you can think of it as the available RAM as being split in half for the stack, half for global variable storage. So a push operation should decrement the stack pointer and then copy data to the stack pointer address. A pop reads the data from the the stack pointer address into a register and then increments the stack pointer. So the stack pointer should always be pointing to a data item that's on the stack. Then you push a new data item, it decrements the stack pointer first, and then copies the data value there. So let's look. Here's a before picture, and then we'll look at some push and pop operations. So let's say R0 is 1, R1 has the value 2, R2 and R3 are both empty. And then I'm going to draw some pictures here of, say, the stack pointer is initially here. Now, I said it's growing down in memory, so this would be a higher memory address at the bottom and a lower memory address at the top. It's typically how we draw it, right? Lowest memory address up here, higher memory addresses at the bottom. So let's say we push R0. And you do that with this notation. So that would result in the stack pointer is decremented first, and then the contents of R0 then are copied into that memory location. Now, fortunately, the linker takes care of initializing the stack pointer for us, initialize it to the start of RAM. We never have to worry about where it is. Actually, you can print out the stack pointer location at any time. Just copy it into register 0 and call print int or print hex to see the stack pointer value or the corresponding memory address. Push, maybe we'll do that as an exercise. Push R1. So this is RAM now. So you can use the stack as freely as you want to in your assembly language programming. Okay, it's supposed to have, I'm just showing 4 32-bit words here. Okay, then the stack pointer would be decremented, and 2 would be there, 1 would still be there. You know, whatever is here is still here. That location of the stack. Okay. Now, if we, let's say, pop into R2, what this means is copy the value that's pointed to by the stack pointer into register R2. So the 2 would still be on the stack, but we're not actually pointing to it any longer. I mean, the memory is not cleared. And then we could pop R3. And the stack pointer would be pointing back to where it was previously. There's no requirement that you have to pop back into the same registers that you push from. You could, but that's not a requirement. So the after picture would be like this. After these 4 instructions, R0, R1, R2, and R3. Be 1, 2, then I popped off the 2, then I popped off the 1. So the instruction sequence here would follow the arrows. First instruction, second instruction, third instruction, fourth instruction. And you can push and pop multiple registers. Remember in this brace notation, it's a register list. We can have like R0 through R3. You always want to make sure if you're using the stack inside of a function that you write in assembly language, that you leave the stack pointer pointing to the same address as it was before you started doing any push and pops. In other words, the number of pops and pushes should always be equal inside your functions. You want to leave it pointing to exactly the same place, because typically what happens when you make multiple function calls, one function may be pushing stuff onto the stack. That makes a function call. That function then will take up right there and push additional stuff onto the stack. It needs to pop it off so that when you return back to the previous function, it knows it's pointing to the data it held. Okay? It knows what's on the stack. And then it can pop stuff off. You can continue to make function calls. I know probably an exercise you write in C is doing recursive functions with local variables. Every time you make a function call, additional data is pushed onto the stack, Eventually, if you don't have some break condition in your recursive function, you run out of memory. You run out of stack space. Okay? You get some sort of error. Your program will crash. Okay, let's actually do another assembly language programming exercise. We're going to implement that random number generator. In assembly. And the random number generator, the code for it was actually pretty simple. Actually, this is what we did, I think, in C. Typically with the random number generator function, it would just return the next random number. We had it actually in a while loop, so it was continuously generating random numbers. And Three, 9, 0, 4, 2, 2, 3. Of course, getting a good random number generator depends on what constants you use here. The good random number generator should cycle through all possible numbers in the 32-bit range. And I think in the C program, we printed out the value of them after we generated every time. And we'll talk about function calls on Monday. I think that on Monday, I actually plan to finish up chapter 3. We have an exam, I believe, a week from today. So we're a little bit behind the schedule. I'm not concerned about that, actually. It was just a pure guess as to how far we would get. But I just delayed the exam in here from Wednesday because we have an electromagnetics exam on Wednesday. So I delayed the exam in here until Friday. So bring up Code Composer Studio and then I'll give you a few minutes to bring it up. Then we'll just copy an existing project that some of the program example we have now is the one that's most complete that has variables, although I don't think we will use variables in this particular exercise. So just copy that project and paste it back into the workspace. I'll call it some random So let's see. You can do this with M as a global variable. Let's go ahead and do that. Okay, so we wouldn't have to. We could keep everything actually just in registers or on the stack. So in this, we had a var x. Now it's M. We'll actually just initialize it. I'm going to set it to 0. We'll initialize it inside our main function. You could set it to 1 here, but we'll go ahead and initialize that inside our main function. Now, we also need a pointer to M. Now, this will actually be a constant that will be in our program memory because it's in this text section. It's a funny word. It sounds like text is where you should have, text files. But in the object code world, text actually stands for where your machine code goes. It's where your program text goes, or program code. Now, the other thing, we're not going to need these strings, but we are going to want to store. There's a number of different ways to do this, but working with 32-bit constants like this, the easiest thing to do is actually just store the constant somewhere in program memory. Those two constants. So we can call the first one a multiplier constant, MC, and then bits. And then I'll just type in the value directly in decimal. And so that's how it's given. 1664525. And then you have to specify the number of bits to set aside. And then we'll have the addition constant. $101, 390, 390, 4223. And then we can get rid of these other two strings. Okay. Those strings were actually stored in memory. Okay. Now here's our main function. It looks like when we load the programs in here, the debugger automatically stops the watchdog timer for us, but later on, it's probably good practice to leave this code in here where we stop it. We do need to initialize the output if we're going to print anything out. The other thing that we need to do actually is initialize the value of M. So I have to load, I'll put it into R0. I have to load the pointer to M. And then I have to get a 1 somewhere. So I'll move a 1 into R1. And then I can store that back in R1 and then R0. Actually, I've got a mistake. For the constants, I want to load that. That's not by reference. That should just be pointer n. Okay. So what I'm going to do here is actually just eliminate all my code and see if I can compile. Leave the branch at the end. I want to make sure that I've only written 3 lines of code, but there's no sense in writing 100 lines and having an error in these 3. So did it compile? It didn't, or did it? So I've got some errors. Some random. What the heck is that? Oh, that's because it should just be main here, not. That was a bug before. I don't know why it didn't. Instead of a sum.
I compiled 5 of the ASM.
ASM main.
Yeah.
I must have another.
Your fault, except
Oh, thank you. Okay, so at least that's compiled now. Okay, and I think, you know, it wouldn't be. So I think we've stored one into, now inside our while loop, what we'll want to do is actually load the value down. Let's see, I probably want to, outside my while loop, go ahead and load those constants so that there's no need to load them every time in the while loop. I am in the while loop going to call like the print routine. So I don't want to load them into R0 through R3 because I'd have to save them on the stack every time. But I can load them into, let's say, R4 and R5. So might as well do that. Let's see. So load. I don't really need. I'm going to reload the address for M every time. So I'll go ahead and, what's the multiplier constant? And then now load R4 from that address. And then load R5 I actually have to load the address first, so the additive constant, and then load into R5 the actual value of that constant. It wouldn't be, probably was not a bad idea at this point. So let's go ahead and check that we've done this correctly. So what I would suggest here, I'm supposed to in order to print it, I actually have to move R4 into R0 and then call print int, because print, and it's not call, it's BL, because print int only prints the value that's in register 0. So we'll go ahead and repeat this for the second. Well, we'll just go ahead and do this. Compile this, see if it, I have to hook up my microcontroller. This is typically the way I program, by the way, is just a couple lines of code because I make a lot of mistakes. I hate it when students come up to me, they've written 300 lines of code and the first line has a syntax error. It's like, how did you, there's no way that any of this is going to be right if you've got a mistake in the first line. So this is what I recommend. Just write a few lines of code, check the results. Go ahead and bring up Putty here. And you don't have to use it, you can use the built-in. Okay, and then now see. "15 minutes later. It's still, did it work? Still waiting for mine to load. Didn't see it. I'm not seeing anything in mine. They want to get anything out. Let me see if I'm actually got the rate. This is supposed to be. That's right. Well, I'll play around with it over the weekend, see if I can get it fixed. And we'll continue on Monday. I haven't actually looked up the difference between, in fact, the tendency uses field for this, but I haven't looked up the difference between fields and bits. I don't think there is one.